Hey everybody, so we're going to be talking about, patterns and conjectures, not consequences. And a conjecture is an unproven statement that is based on observations. Now, this definition is different from the one that I had you write in your vocabulary, and that's just so that you have different ways of understanding it. So, pretty much, based upon what you see, you can make a conjecture based upon your observations. And when you're writing a conjecture, what you're doing is you are going to use inductive reasoning. And you use inductive reasoning when you're finding specifically a pattern in cases, and you're going to be writing a conjecture for the general case. In other words, it's a type of reasoning that reaches conclusions based on a pattern of specific examples or past events. And you actually use inductive reasoning every single day, but just didn't know that's what it was called. Right now, there's always, well, not always, that alone could be used against me. Um, when you're when you're having like an argument or a very healthy discussion, all of this logic that we're going to be using this chapter is going to help you. Okay, you'll also use it in philosophy class. So, a counter example here is a specific case or example for when you take a conjecture and make it false or prove it false. Pretty much, hey, yeah, you're telling me that this is always true, but here's an example of when it's not true. And what we're going to do is we're going to go through all of these, and I've got 3 different sections that we can cut through in this. For the first set of examples, all I'm going to ask you to do is to find the next 2 terms. So you have examples A, B, C, and D, right? And pretty much we're going to find the next 2 terms. You'll notice for A, it goes 1 on the bottom layer, 2 on the bottom layer, 3 on the bottom layer. So that's why for this next one I drew 4 on the bottom layer and moved up. And then now I'm going to add another layer, which is a 5th layer, and do everything. And I have my next 2 terms. Alright, for B, from 3 to 9, you'll notice that we're multiplying by 3. 9 to 27, multiplying by 3. 27 times 81, multiplied by 3. So we're going to do 81 times 3, which will get you 243. And we're going to take that and we're going to multiply that by 3, which gets us 729. And so these 2 will be the appropriate answers for the next 2 terms. So I'm going to go ahead and put a box around this, or try to. And then you know what I just realized? I did not box my other answers in part A. So there we go. Kind of jankety, but we'll be okay. Now let's look at C. C is a little bit different. So I see one thing. It goes from 1 to 4. I'm adding 3. Alright. And then from 4 to 9, I'm adding 5. And 9 to 16, I'm adding 7. Which means the next number I would add would be 9, which gets me 25. And then from 25, I would add 11 to it, which gets me 36. Pretty much I'm adding consecutive odd integers. 3, 5, 7, 9, 11. And the next number I would add would be 13, by the way, to get my 3rd term. For part D here, notice all I'm doing is I'm subtracting 8 each time, even though it goes from positive to negative, and it stays in the negative. So all I'm doing is subtracting 8, which means my next one would be negative 24, and then negative 32. So these are the patterns, and these are the conjectures that you have found based upon the examples and the history. Right now, you've used inductive reasoning, and we're going to write the conjecture. A conjecture is a statement, so you have to write words about it. We're going to focus on parts B, C, and D. Now I want you to look at part B. All we're doing is we're multiplying the previous term by 3. So that right there, that's your conjecture. In geometry, you are going to start writing a little bit more, right? You're using your words to explain what is happening. All of these years you've been doing the math, but you need to be able to answer the why. Why is it happening? How is it happening? And use this logic whenever you need to win a discussion with anybody. All right, now let's look at C. The first one we saw, and we talked about this, is that we are adding. I'm going to switch colors so it's a little bit easier to see. We are adding consecutive odd integers, right? And we saw that with the 3, 5, 7, 9, 11. But there's also something different. And the different one is, and it won't always be the case that you have two conjectures, but it can, is that it's a term number squared. So pretty much it's the first term, which is 1 squared. Then it's the second term squared, 2 squared. Then it's the third term, so that's 3 squared, 9. Fourth term, 16, which is 4 squared. Fifth term, 25, and so forth. And then for D, we already talked about this. All we were doing is that we were subtracting 8 from the previous term. Now, these go together. Example 3, right? This is where I'm going to show you how to find a counterexample. So for example, if the name of a month starts with the letter J, it is a summer month. Okay, so we know we're looking for a name of a month. It has to start with the letter J, and that means it is a summer month. Well, let's find something that makes it false. Think about the months. We've got... Well, let's work backwards from where we are. We've got June that just happened. We also had July just happen. I think. Oh, wait. We also have January, and that is not a summer month. And it's a month that starts with the letter J. This is saying that if it starts with the letter J, it is a summer month. Well, that's not true always. January is your counterexample. January proves that person wrong. Now this next one says that the square root of a number x is always less than x. So pretty much the square root of x is going to be less than x. Always. Now whenever you see words like always or never, typically those are going to be your ding 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 ding. You're probably going to be able to find a counterexample. That's not always true, of course, but a majority of the time that is true. So pretty much what this one is saying is that the square root of 9 is equal to 3, and that 9 is less than 3. Same thing with the square root of 4, it's less than equals 2, which is less than 4, 25, which is less than 5, 36, which is less than 6. But if we keep going backwards, we'll notice that the square root of 1 is equal to 1. And 1 is not less than 1. 1 is 1. So this right here would be a counterexample.